How do we write Lewis structures for covalent compounds? We're going to give you some guidelines, but then this involves some practice and some figuring it out. It's like I could give you steps for riding a bicycle, do this and this and this, but it would require some practice, and you kind of have to get the hang of it right. You have to develop a sense of balance, and that's a little bit what writing Lewis structures is like. Guidelines are helpful. So first, we're going to write the correct skeletal structure, which means we're going to write down the symbols for the atoms of the different elements and figure out how they're arranged with each other. And there are guidelines. Hydrogen, remember, can only form one bond, so hydrogen is always going to be terminal, meaning on the end, attached to only one other atom. You can't have hydrogen in the middle bonding to two other atoms because it just can't do that. It doesn't have enough electrons. Many molecules tend to be symmetrical. So if you've got a molecule that's got like 4 oxygens and 1 sulfur, that odd one is probably going to be in the middle and the other ones are going to be arranged around it. There are lots of exceptions, and we're going to try to stick with the more straightforward ones. But just as a general rule, they tend to be symmetrical. Then we're going to figure out how many electrons do we have to mess around with. So you're going to look at each of the atoms that you have and figure out by looking at the periodic table how many valence electrons does that atom have. And that's going to be the number of dots that it brings. And we're not going to think about, well, this atom brought this many dots, and so they're going to pool their dots all into a pile, and then we're going to divide them up so that everybody gets happy. We're going to share them. It's a little bit like boys bringing cookies, and we're going to make just one big plate of cookies, and then we'll go around and we'll make sure everybody gets the right number of cookies. So main group elements, number of valence electrons is just the number of its group. If we have ions, you need to add an electron for a negative charge and subtract for a positive charge. And that can be a little confusing sometimes. But just remember that we're changing the number of negative charges, we're not changing the number of protons. If I take away a negative charge, then my ion will be positive. If I have a negative ion, that means it's got some extra electrons. Then we're going to take those dots and we're going to spread them around all the atoms and try to get everybody an octet or a duet for hydrogen. So there has to be at least one bond between atoms. So you need to have 2 electrons between each atom to make a bond. And then you put the rest of them around. Sometimes there's not enough. When there's not enough to go around, then we have to share more. And that's when we have double and triple bonds. And we do that by taking the lone pairs and moving them into sharing them as bonding pairs. And we're going to do a bunch of examples. Let's write the Lewis structure for carbon monoxide. So the first step was just to figure out the arrangement of the atoms. Well, this one's pretty simple. There's 2 atoms. They've got to be bonded to each other, right? So we'll put the carbon next to the oxygen. There's carbon, and there's the oxygen. It doesn't matter if you put one on top of the other or which one's to the right or left. It's just a picture. It's a drawing. And then we need to figure out how many valence electrons do these atoms have. How many valence electrons does carbon have? It's group 4, so it has 4, and oxygen has 6. So 4 plus 6 is 10. So we have 10 dots that we can mess around with on this Lewis structure. So we're going to start by putting a pair of electrons between the atoms. So there's 2. And then we're going to start spreading them around. 2, 4, 6, 8, 10. I ran out of dots. I ran out of electrons. Does each of these atoms have an octet? No. So this is where we need to make double or possibly even triple bonds. What we can do is I can take one of these lone pairs and pull it in here. I'm not making more electrons, I'm just moving some. It's like, okay, oxygen and carbon, you're going to need to share a little bit more. So, what am I doing? I'm going to put those in here and erase them from right there. I still have 10 electrons. Are these guys happy yet? Is one of them happy? Is carbon happy? 2, 4, 6, 8. These are bonding electrons. Oops, I did not mean to do that. That's what undo is for. So this is a bond, and this is a bond. So the carbon's counting 2 lone pairs, 2, 4, 6, 8. Carbon's happy, oxygen's not happy. Oxygen's thinking, hey, I threw in my lone pair of electrons, and now you're great with 8 electrons, but I'm still short over here. Toss yours in. So what we need to do is we need to take another pair of another lone pair and bring them over here to be a bonding pair. So we're going to move those in here. And then just to show that that's a bond, I'm just going to connect the dots. Now this carbon counts 2, 4, 6, 8, and the oxygen counts 2, 4, 6, 8. They each have 8 electrons. We've got the correct number of electrons, and there's our Lewis structure. Sometimes you make a mess when you're drawing the Lewis structure, and so you may want to copy it over more neatly. And when copying it over, it could end up looking like this. Well, that's a little tidier, right? Same thing. Any questions? Let's do H2CO. H2CO. So we have to figure out how to arrange these guys. A lot of times the formula is going to give you a clue, okay, by the order. So how could we put these together? We know that the hydrogens can't be in the middle. So the carbon and the oxygen must be in the middle somewhere. Carbon and oxygen in here. And then H2C, maybe the 2 hydrogens are bonded to the carbon. So we could put one over here and one over here. And that's just kind of a skeleton arrangement. We can't do something like this because hydrogen can't do that. It can't share with more than one atom. It can only share with one at a time, so we can't do anything like that. How many electrons do we have to mess around with? How many does the hydrogen have? There's 2 hydrogens, and they each have 1, so that's a total of 2 from the hydrogens, and carbon has 4, and oxygen has 6. So that gives us a total of 12, right? Sometimes I do my math a little too creatively. So first thing is, we need a pair of electrons between the atoms, because there has to be at least a single bond. Otherwise, it wouldn't be a molecule. It'd be just some atoms who are maybe in the same beaker or something. So 2, 4, 6, 8, 10, 12. I ran out of electrons, didn't I? Hydrogen's good. This hydrogen's good. Hydrogen's always happy with 1 bond. This carbon is good. He's happy. 2, 4, 6, 8 electrons. Oxygen has 2, 4, 6. The oxygen's not happy. That means we have to take a lone pair and make a double bond. If I take one of oxygen's lone pairs and stick it in here, that's going to give carbon too many electrons. It's good as it is right now. It's got 8. So we need to take the lone pair from carbon and move it over here. Carbon will still have 8 then. So I'm going to put those over here. Just going to connect those. Those are bonds. And now the carbon has 2, 4, 6, 8. The oxygen has 2, 4, 6, 8. And everybody's happy. If I rewrite that, it might look something like this. Any questions? We can write Lewis structures for compounds. We can also write them for the polyatomic ions. Remember, polyatomic ions are atoms that are bonded together. They have covalent bonds holding them together, but overall the group of atoms has a charge, and so it's an ion, not a molecule. So we need to pay special attention to the charge of the ion. Again, adding electrons for negative charges, subtracting for positive. And then we're going to show the Lewis structure for that ion within brackets and write the charge of the ion in the upper right corner outside the brackets. Can you do brackets in Mastering Chemistry? No. Mastering Chemistry doesn't do brackets. So let's do the cyanide ion. Cn minus. Well, this is a simple one. It's got 2 atoms, so they have to be next to each other. That's the skeleton. Then we need to identify how many valence electrons, how many dots can we play with here. Carbon has how many valence electrons? 4. And nitrogen has 5. What do we do with that negative sign? That means we add 1 electron. It got to be a negative ion by gaining an electron. Electrons have negative charges. So we're going to add 1 for the charge, and that's going to give us 10 electrons. So we'll put a pair between. There's 2, 4, 6, 8, 10. Ran out of electrons. So we're going to have to do some extra sharing. So we'll move a pair into the middle. I'm going to connect these so that we can keep them straight. Does everybody have an octet now? No. Carbon does, but nitrogen doesn't. So we need to share some more. So carbon's the guy who's satisfied, nitrogen is not, so carbon's the one who needs to share a little bit more. So we're going to take a pair of electrons from carbon, and he's going to share them with nitrogen. There we go. Now does everybody have an octet? Yeah. This is an ion, so we need to put brackets around the whole ion and put the charge on the outside. And if we clean this up a little, it might look like this. Any questions? Anybody remember the name of this ion, ClO minus? It's related to chlorate, which is ClO3 minus. Chlorite would be ClO2 minus. It's one below that. Hypochlorite. That stuff's not going to go away. If you don't have that down, and it sounds like you don't, you need to keep working on that. So this is another one with just 2 elements. So there's Cl and there's O. And we need to identify number of valence electrons. How many does chlorine have? 7, and oxygen has 6, and the -1 charge causes us to add 1, so we get 14 valence electrons. We're going to start out by putting a pair of electrons between to be the bond. So there's 2, 4, 6, 8, 10, 12, 14. Does everybody have 8? Yeah. This one's easy to see because we've got top and bottom, left and right. Top and bottom, left and right. They've both got 8. And then we need the brackets and the charge on the outside. Any questions? There are exceptions to the octet rule, of course, right? That would be too simple. There are some molecules for which it is impossible to write good Lewis structures, and yet they do exist in nature. Yeah, I know I might want to. I do want to, but I can't plug it in because I left the charger at home. There, we'll do that. Maybe with the screen really dim, we'll go better. Okay, so if we have something like NO, it's got an odd number of electrons. You can play with that all day, and there is no way you can make it come out so that each atom has 8 electrons. We'll just do the best that we can. The best we can do is for oxygen to have 8 and nitrogen to have 7. That's the closest you can get. Another exception is boron. Boron is one of those little guys. He's not as small as like lithium and beryllium to just go with the duet rule, but he's still pretty small, and so he often forms compounds in which he just has 6 electrons. So boron trifluoride or boron trihydride, these are compounds that exist, and they do not obey the octet rule. So boron just, he's easily satisfied. If you give him 6 electrons, he'll be good with that, and he'll leave you alone. Another way that can happen to have an octet rule violation is we can have molecules like SF6 and PCl5. Here, instead of having fewer electrons, we have extra electrons around the central atom. Here the sulfur has 2, 4, 6, 8, 10, 12, and phosphorus has 10. These are called expanded octets because we've grown from 8 to 10 or 12 electrons. I want you to know that exceptions to the octet rule exist. That's about as far as we're going to go in talking about them. You just need to know that they do exist. But even with those exceptions, Lewis theory is still a really helpful way to understand chemical bonding.